Hello, it's me again, and we are still in the process of understanding the different hyperparameter search algorithms. So we've already covered random Monte Carlo and also grid search and population-based training. And what all those have in common is that they can't actually learn uh, from experiments which already have been done. So there is no way of incorporating previous knowledge during the hyperparameter optimization process. And another way of doing that, so that's basically model-free learning or model-free optimization. And another way of doing it is using a model. So today I want to introduce Bayesian optimization for hyperparameter tuning. And first of all, we need to understand the Bayesian statistics. So let's introduce Bayesian statistics. So if you go back, so a probability distribution is basically a function where you have as an input, you give it a specific outcome, and what you get back is a probability value for that outcome. So for example, let's say you have a function, the probability of that it is raining at a specific day, and the input is the day of year, for example, and what you get back is the probability that it will rain at a specific day, and that obviously can be trained and learned from past data. So now it's consider a house and a garden and automatic water hose, and given that you have grass on top on front of the house, and the grass can be wet, so there's then also a probability the grass being wet either through the automatic water hose or when it was raining. So you can also create a probability distribution for the fact that the grass is wet. So P grass is wet given a specific day. And now if you have prior knowledge about the fact if it was raining or not, the probability obviously changes, because the probability if it was raining before that the grass is wet is obviously higher. So that's where this Bayesian magic comes in. So what you can do in Bayesian statistics, you can lock in a probability function with additional facts, and in that case you can lock in the fact that it was raining. So the probability of the grass being wet is one probability distribution that is called the Breyer distribution, and then the probability of the grass being wet given that it was raining is the posterior distribution. So you write it basically P for probability, the function is P, the distribution function, and as parameters you usually have then the actual fact, then vertical bar, and then the fact you lock the function in. So for example, the grass is wet, the vertical bar, given that it was raining today. Okay, so then there's the Bayes theorem, which basically allows you to swap the probability lock in. So let's say you have a probability P of A given B. You want to know the probability of A given B. So for example, the grass is wet given it was raining. So that's something you want to know, and you only have the probability of the rain, if there was rain, and you have the probability of the grass is wet, and the conditional probability of the it was raining given that the grass is wet. So that actually means P of A given B equals P of B given A times probability of A divided by probability of B. So that's the Bayes theorem. And the whole purpose of the Bayes theorem is basically of swapping. No, if you want to know P of A given B, and you have P of B given A, and you have the probability of A and the probability of B, then you can compute the inverse. Okay, so that's all about Bayesian statistics so far. And now, when we come to hyperparameter optimization in grid search and in Monte Carlo random search and also in population-based training, you basically just evaluate different points in that multidimensional or hyperdimensional optimization space. But you actually cannot draw any conclusions from prior knowledge. So if you have evaluated one point and you get a certain loss for that point in that hyperparameter optimization space, you have not a good way to find out which other point you want to evaluate. So that's where Bayesian optimization kicks in. So 95 or 99% of the Bayesian optimization is done using a so-called Gaussian process. So that's nothing else than fitting a normal distribution. And as a data scientist, you should always be really careful if someone is talking about using a normal distribution, because that's stuff the ordinary statisticians are doing, not the data scientists. We are having the better models, no? But anyway, so how it is done is, as far as I understand, is that given the already evaluated points in that hyperparameter space, you train a Gaussian process. So you basically try to parameterize a normal distribution, and that will allow you to make assumptions on the loss of future points in different positions in that hyperparameter optimization space. And not only that, in addition, you will also attach to that get a confidence interval per point. And obviously, the closer the already evaluated points are, the smaller that confidence interval gets. So, or let's say the uncertainty gets smaller. And so that's one thing. No, you first have to understand, in contrast to the grid search, random search, population-based training methods, you actually have a model which you train during your exploration, and that model will help you in optimize the future choices of hyperparameter configurations to evaluate in future. So that's the whole thing in a nutshell. So, and now you have this, and it's an ongoing process. This Gaussian model, this will be improved. The more points you evaluate, the smaller the uncertainty gets, specifically at points close to already evaluated points. And now the whole thing is actually a little more complicated, because now from this Gaussian model, you have to actually decide which future point in the hyperparameter optimization space you want to evaluate. And in order to do that, you have to compute a so-called acquisition function. And the acquisition function is also a hyperparameter. So it's there are many acquisition functions possible. And it's basically a transformation from your Gaussian model to another function. And once you have done the transformation, this other function will help you in recommending you the next point to evaluate. Yeah, that's all for now. Maybe one final thought is, we talk a lot of parallelization, which is beneficial. And in the case of random grid search, population-based training, it doesn't really matter the amount of parallelization. But in Bayesian optimization, it's actually better to have a lower parallelization, because each evaluation of the model, so each evaluation of the underlying model you want to tune with your hyperparameters, is actually helping you in improving your estimates for the future hyperparameter points you want to evaluate. Therefore, it's actually better, in case you are having a cluster, to parallelize the actual training and as less as possible parallelize the actual Bayesian optimization steps. Yeah, okay. So if you have questions, leave them down in the comments, and I will give you an update, maybe a little demo about the Bayesian optimization program running on my cluster, to see actually how this works. Bye.